Polynomial is lambda minus 3 twice, multiplies to 0. I got lambda equals 3 and 1, 1. And I can factor this as an S inverse. And I'm going to talk about what that J matrix is like. So if it was a diagonal matrix, we would have 3's on the diagonal. And what's the one thing Jordan did to make this work? So the Jordan matrix is going to be very close to a diagonal. It's going to be like that. If it was 3 by 3, well, if we have time, we'll talk about that. That's the closest that Jordan can get us to a diagonal for a 3 by 3 case. So it's almost diagonal. It's just above here. Sometimes you've got to put a 1 instead of a 0. So we'll focus on the 2 by 2 case. So there's a couple.
For example, we're doing 2 by 3 as well, or not?
Possibly.
Possible.
Yeah, actually, well, I'll add up. How do you run?
If you said focus, I wasn't sure which one.
Say it again?
When you said focus on 2 by 2, I wasn't sure which one.
Oh, just for this particular example. So I want to start by going on the 2 by 2s, and then we'll talk about 3 by 3s when we have time. Yeah, we are making, I feel like we're making good time. We can do some 3 by 3 examples. So this is more important than anything. So remember, we set up our equation like this to find the eigenvectors. And then it is in a slightly different way. So this is going to go back to how we first set up subtracting lambda from the main diagonal. So this is the way most people teach the eigen stuff. Is we want to factor an xy out. And to get the dimensions to work out, you have to multiply by this. So a slightly different way of saying that xy has to be an eigenvector for lambda equals 3 is to say that xy is in the null space of this matrix. And where this matrix came from was the A minus lambda I. So a slightly different way to calculate eigenvalues and eigenvectors is to work directly with the A minus lambda I form. So just as a warm-up. What's this? Set myself up to find the eigenvalues. The algebra is not very interesting here. subtract lambda from the main diagonal, compute the determinant, the AB minus BC, work it all out, factor. And then what I'm going to do is, my new method is plug the lambda equals 3 into this, and then find an interesting vector in the null space of that matrix. So if lambda equals 3, what's the first column? Okay, then, essentially we've pre-subtracted the x and y part from both sides. Same equation as promised. And then you just have to give me an x and a y that work. What do you think? Excellent. Okay, so again, I can just plug, instead of doing my original matrix times xy is eigenvalue times xy. And then when I multiply it out, subtract the 3x and 3y from both sides. So I actually did the subtraction right here. And let's do another one. So I'm going to plug lambda equals 1 into this matrix. It's a lot of ones. And the xy is going to be the null space of that matrix. So same equation twice. Perfect. So for the Jordan form, is we're going to focus on this way of finding the diagonal space. I'm going to do this abstractly. This is the one where we got the eigenvalues both equal to lambda. And we got the same number twice, just like the previous one. What's the J matrix going to look like?
Number 1,
So Jordan showed us that's the closest we can get to a diagonal matrix and still have this work out. And we're still going to build that S as a column of vectors. I just want to see what vectors we need to make the S work. JS. I didn't approach it this way very often because I like the change to the new basis, transform, and then change back to the original. But there's another way to look at what we're doing here. Is if I right and multiply both sides by S, remember that the order matters when we multiply. So if I start with A times S and then switch the order, I can keep the S here, but that's going to be a different matrix. So what I'm going to get is when I do A times the S matrix, that's going to be the same thing as S times the J matrix. And what I'm trying to do is figure out how to get the V1 and the V2 based on the A and the lambda. The A was given to me at the start of the problem. As I worked through this whole mess, and I got the lambda. So now, I want to figure out how to get V1 and V2 based on those. Here. So remember, our first matrix multiplication was matrix times the column. And then we did matrix times matrix. And what we saw is each column of that answer matrix was just what we did as matrix times the column. So this has columns like that. And on this side,